The relative isotopic mass is the mass of an element in relation to carbon-12. The reason that this is the isotopic mass is because some elements have different isotopic forms. For example, chlorine can be found as chlorine-35 and chlorine-37. The isotopic mass is not the mass number which appears on the periodic table. The number seen on the periodic table is the relative atomic mass, or the AR. The relative atomic mass of an element is defined as the average mass of the naturally occurring isotopes of the element relative to the mass of an atom of carbon-12. On the periodic table, it is the same number as the mass number. In basic terms, it is the average mass of the isotopic forms of the element. When we think about this, we must remember that isotopic forms of elements have different values for their naturally occurring abundance on Earth. For example, let's look at the isotopic forms of chlorine. Some chlorine atoms have a mass of 35, and some have a mass of 37. In most cases, to take a simple average, you would just add the values together and then divide by the number of values. In this case, it would be 35 plus 37 divided by 2, and you would get an average of 36. But this is not how you calculate the relative atomic mass. We need to remember that we are talking about number of atoms. There are a certain number of chlorine atoms with a mass of 35 and a certain number of chlorine atoms with a mass of 37. However, within a sample, the levels of each isotope are not equal. So we take this into account when we are calculating the relative atomic mass, so that we are calculating a weighted average. Naturally occurring chlorine is made up of 75% chlorine-35 and 25% chlorine-37. This can be shown to you on a graph to show abundance data, where the relative isotopic mass is shown along the x-axis and the relative abundance is shown on the y-axis. So say we had a simple sample of 100 atoms of chlorine. We would have 75 atoms of chlorine-35 and 25 atoms of chlorine-37. We first find out the total mass of the sample. We do this by multiplying the mass of each atom by the number of atoms present for each isotope, and then we add them together. For chlorine-35, there are 75 atoms, and for chlorine-37, there are 25 atoms. So the mass of 100 atoms would be 75 times 35 plus 25 times 37, 3,550. The mass of one atom will be the mass of the total number of atoms divided by the number of atoms. So the mass of one atom of chlorine would be 3,550 divided by 100, 35.5. The relative atomic mass has a value closer to 35 because there are more atoms of chlorine-35 than chlorine-37. It is a weighted average. So the relative atomic mass of an element is defined as the average mass of the naturally occurring isotopes of the element relative to the mass of an atom of carbon-12. On the periodic table, it is the same number as the mass number. The number is a weighted average, and when calculating its value, the proportion of an isotope in a sample must be taken into account.
Welcome. In this biology lesson, we will be learning about every chemist's favorite animal, the mole. We will see how the mole connects the world of atoms with the world of measurements in a simple and intuitive way. Without further ado, let's dig in. Up to this point, we've been calculating atomic and molecular weights using atomic mass units. However, atomic mass units measures the mass of a single atom. One atom has such a teeny tiny mass that AMU are not really useful to measure anything else. Can you imagine a conversation about breakfast like the one on this slide? Trying to measure real-world objects using atomic mass units would be ridiculous. When chemists have to measure the mass of real-world objects, we prefer to use the mighty gram. However, since atoms are measured in atomic mass units, we'd need some sort of conversion factor to go between atomic mass units to grams. The number 6.022 times 10 to the 23rd is just that conversion factor. It's the number of atomic mass units in 1 gram. This number has the nickname 1 mole. The word mole is just human shorthand for a specific number. In the same way that the word dozen symbolizes 12, the word mole symbolizes 6.022 times 10 to the 23rd. The mole is also called Avogadro's number after this handsome fellow. Interestingly, Avogadro never knew the value of a mole. It's named after him because he predicted that one number could convert between microscopic and macroscopic masses. How big is a mole, you may be wondering? A mole is very, very big. A mole is a trillion. If we gathered a mole of basketballs, it would have the same volume as the Earth. If we counted to 1 mole of seconds, we would be counting for 190 trillion centuries. This comparison really blows my mind. Astronomers estimate that the total number of stars in the universe is about 1 mole. That's a lot of stars. The number 1 mole didn't just pop into existence. As I mentioned, it's the conversion between atomic mass units and grams. So, while 1 proton weighs 1 atomic mass unit, 1 mole of protons weighs 1 gram. This makes it easy to use the periodic table to calculate the mass of 1 mole of an element or compound. But I'd like to pause and recognize that our tiny human brains have a notorious difficulty working with large numbers like 602 billion trillion. If you're ever feeling overwhelmed by using the word mole in a sentence, you can just substitute the more familiar word dozen. It's much easier to think about things in dozens. In section 3.2, we learned that the formula mass is the mass of 1 molecule of a compound in atomic mass units. Molar mass is a very similar concept. It's the mass of 1 mole of compound in grams. So, the atomic masses on the periodic table represent the mass of atoms in AMU, and they also represent the mass of 1 mole in grams. It's the exact same number. We calculate the molar mass in the same way that we calculate formula mass, by adding up the masses of each element in the compound. Pause the video and practice calculating the molar mass of oxygen as well as sulfur dioxide. Recall that oxygen is a Brinkelhoff diatomic, so the molar mass of oxygen is 2 times the molar mass of an oxygen atom, or 32 grams per mole. The molar mass of sulfur dioxide is 2 times the mass of oxygen plus the mass of sulfur, or 64 grams per mole. You will be calculating lots of molar masses in this class, so keep a periodic table close by. This image shows 1 mole of some familiar substances: copper, water, table salt, sucrose, and aluminum. Each of these samples has a different mass, but they all contain the same number of entities, which is 602 billion trillion, or 1 mole. You can see that the amount of this substance is much easier to work with and might be close to something we'd use on the laboratory scale. The purpose of the mole is to be a conversion factor, which allows us to go from individual entities to grams. During Chem 101 and Chem 102, you will regularly convert between grams and moles. The top 2 conversion factors will be the bread and butter of a process called stoichiometry. However, it's rare that we want to know how many individual entities a certain sample has. These bottom 2 conversion factors will only be used sparingly, such as on the next practice problem. Okay, pause the video, see if you can answer these questions about sulfur difluoride. To calculate the molar mass of sulfur difluoride, we first need to know the formula of sulfur difluoride, which is SF2. To calculate the molar mass, we'll take the mass of 1 sulfur and add it to the mass of 2 fluorines. Sulfur dioxide weighs 70.1 grams per mole. To convert 100 grams of sulfur difluoride into moles, we need a conversion factor to go between grams and moles. Luckily, the molar mass we just calculated is the perfect conversion factor. Be sure to flip the fraction so that grams is on the bottom and our units cancel properly. To convert from grams to individual molecules, as in the last question, we need 2 conversion factors. We'll use the molar mass first, but then we need to convert from moles to molecules using Avogadro's number.